So if we flip over to our Excel file for lecture 14, the first thing we're going to do is we're going to do rectangular integration. And the rectangular integration, so we're going to do, all three of these examples we're going to do on this function, which is shown inside the integrand as 3x cubed minus x squared plus 2x plus 1. So it's a polynomial. And we're going to integrate from x equals 0 to x equals 4. In this rectangle approximation, we will look at the integral approximation for if we have 5 points, in other words 4 subintervals, or if we have 9 points, i.e. 8 subintervals, etc. And I think this one is 40 subintervals is a third one we're going to look at. So what does that look like? So in the first one, since it's the rectangle approximation, the area of this first subinterval is equal to f of x 0, or the first f of x, this would be the left-hand approximation, times the interval xi plus 1 minus xi. Or you can think of it as xi minus 1, either way, depending on what you call I. Okay, so that's my formula for the first area of the first subinterval. And what I want to do here is I want to take this area and I want to drag it down. Now I drag it down and I don't actually include the final point because the final point doesn't exist, right? This would be like taking another subinterval after the final point. So we don't have that area. So the first integral approximation is the sum of each one of those sub-areas, and we get 110. It turns out this is not a very good approximation, but we'll get to that. The second formula, it's the same idea as the first one, except for in this particular case, we have more points. They're equally spaced in each case. And I can just go ahead and copy the formula from the first one and paste it into the second one. And it's the same formula, it's just that now we have a more number of points, a larger number of points. So I'll take this area and drag it down. And now we have a different integral. Now presumably this is a little bit better of an approximation because we have more points, and that's actually the truth, yes. Finally, we can take this last set of approximations. Again, you have your f of x I minus 1 times the distance in the subinterval, xi minus xi minus 1. And we can drag that down too, or I can just double click on the little square and it fills down for me. And if I scroll all the way down, what I get is now my, we don't want that last point. Now my integral approximation is 181.58. So we have 3 different approximations to the integral, one being very poor, 110. This one is a little bit better, I'm assuming, and this one, I'm assuming, is the best because we have the largest number of points. And so that would be the rectangle approximation. That's the left-hand approximation in particular. I could also do the right-hand approximation, but I'm not going to. The next thing we want to look at is the trapezoidal rule. So the trapezoidal rule has a different formula for the area. So the area is equal to, in the case of the trapezoidal rule, 1/2 times the sum of 2 f evaluations, f of xi plus f of xi minus 1. And I have to times that by the difference in the x's, or my delta x. So xi minus xi minus 1. And so now I have my first sub area, and I can just drag this down. And so with the trapezoidal rule, with just 5 points, 4 subintervals, you have a still different approximation to the integral. We're still not sure which one's the best. Let's keep going. So if I want more points, that's fine. That's what I have here in this second set of columns. And I can just copy over the formula from the first set of columns, just like I did with the rectangle rule, and then drag it down. And in this case, now I have something that is, okay, so now I have 193.5. And this approximation of the area is probably better than the 202. And if I switch back over to the rectangle rule, it's looking closer to the best rectangle rule that the rectangle rule had to offer, which is 181.58. And it's very different from the rectangle rules approximation when I had 8 subintervals. So compare the 147.5 to the 193.5. They're very different. Okay, finally, let's go ahead and look at what is probably going to be the most superior to this point approximation to the integral, and that would be this this trapezoidal rule with 40 subintervals. And here we have 190.78. So we have 193.5 for 8 subintervals and 190.78 for 40 subintervals. Compare that again to the rectangle rule. The best the rectangle rule had to offer was 181.58. Now, assuming that 190.78 is the most superior one, you actually are off by a pretty large amount between the trapezoidal rule and the rectangle rule. So this demonstrates that the trapezoidal rule is a lot more accurate. Or the difference between the trapezoidal rule and the left-hand side rectangle rule is quite large when you have the same number of points even. Okay, so lastly, that's the trapezoidal rule. And lastly, what we're going to do is we're going to do Romberg integration. Now remember, in Romberg integration, we're going to take 2 different approximations to the integral. And then we're going to add them together in a particular way. So to do that, the first thing we're going to do is I'm going to do, I know I called it A0 and A1, but here we have A1 and A2. It's really A1 and A0. So the first thing I'm going to do is I'm going to do the exact same formula for the trapezoidal rule that I had before. So I'm actually going to cheat and copy that over from the other tab. Same formula that we had before. Drag it down. Good. Okay, the next thing we want to do is this one's a little bit tricky because we have to skip every other subinterval. So this one is going to be a little bit different formula than what we had before. So this one, what we have is the same trapezoidal rule, so it's equal to 0.5 times the sum of 2 f's. But now they're not adjacent f of x's, they're off by 1. So now we have f of x I plus 2 plus f of x I. And the subinterval we're going to multiply by is the larger subinterval, where we're skipping a point in the middle again. Now I can't just fill this down, because if I do, I'm going to get more subintervals than I want. I only want 2 subintervals here, because otherwise we're double counting. And so now we have an A1 and we have an A0. And if we combine them in just the right way, according to this Romberg integration formula, this is just another way to say it, we can pull this C11, or the A1 formula, inside the parentheses, and we get a third times the quantity for C11 minus D11. But I just had this pulled out here, it's fine. Same formula. And we get this 190.667. Now let's go ahead and compare this. Now remember, I'm only using 4 and 2 subintervals here. 4 subintervals for the A1 and 2 subintervals for the A0. And if we combine those 2 estimates in just the right way, we get 190.667. If I flip over to the trapezoidal rule, that's very close to just the trapezoidal rule by itself with 40 subintervals. In other words, I have a lot less calculation to do here, and I get what seems to be very close to the number that is the most superior trapezoidal rule number. Now, I'm not sure at this point which one is better. Is the 190.78 better, or is the 190.667 better? Let's go ahead and see what happens to this number when I increase the number of points for Romberg integration. So I will copy over my 2 formulas in the first row. The first one for A1, the second one for A0. Let me go ahead and fix these headers here too. So for 8 subintervals, now, what is my Romberg integration going to look like? So I'll take my A1 and I'll drag it down. And then I'll take my A0, and what I can do is I can copy, paste, paste, paste here. I can do that. But I don't want to. Oops. There is an easier way to do it. I can highlight 2 cells and then drag down. And what Excel knows when I do this is that it knows that I want to put the formula in every other cell. At least I think this is going to work. So let me drag it down. And voila, that's exactly what it does. So when I highlight 2 cells before I drag down, it knows that I want the formula in one and then skip one. Formula in one and then skip one, etc. And this is exactly what I get. Now what's interesting about this, you didn't have to do it this way, but note that this 202 number is the same as the one that we got over here with only 4 subintervals. And that's because we're using this exact same 4 subintervals as we had before. Same numbers are showing up. At any rate, so we have 4 subintervals for A0 and 8 for A1, and we combine them in just the right way using Romberg integration, and we get 190.667. In other words, when we double the number of points to use in the Romberg integration estimate, we get the exact same estimate up to 3 decimal places as we did when we had only 4 subintervals. Since, presumably, the Romberg integration method with more points is more superior than the one with fewer points, then 190.667 is a better approximation than the previous 190.667. It's just that this superiority in approximation is beyond the 3rd decimal place. You can't even see it in Excel because I have it rounded to 3 decimal places. In other words, the Romberg integration with 4 subintervals, as far as we can tell, is just as good, is just as accurate as with 8 subintervals. And that's because already it's good enough. But let's go one step further. So finally, we will take this last Romberg integration with 40 subintervals. So I'm going to again call this A1 and A0 like I had before. Drag down on the A1, drag down on the A2, and of course we have to delete the final 2 points. And again, we get 190.667. Now notice in each case, the single trapezoidal rule gets better. 202, 193.5, and 190.78. That's not surprising. We've already seen those numbers. They're the same numbers that we saw on the trapezoidal rule tab. 202, 190.35, and 190.78. Trapezoidal rule tab. Back to the Romberg integration tab. Again, 190.667 in each of the 3 cases. What this is telling us is that more than likely, 190.667 is probably actually basically the exact answer. And you got this exact answer up to 3 decimal places with just 4 subintervals using Romberg integration. So finally, the summary tab. What do we get here? So with 4, 8, and 40 subintervals for the rectangle rule, the trapezoidal rule, and the Romberg integration, you see how bad the rectangle rule is. It's not even close to the analytical solution, which, like I said, 190.667. The trapezoidal rule, you just need a lot of points in order to get it pretty accurate. Romberg integration, accurate from the get-go. In other words, Romberg integration, if you combine these 2 trapezoidal rules together in just the right way, you will get a really good approximation to the integral with just a few points. Last thing I want to leave you with, just to make you think about these things, there are a few caveats to this. Remember, when we derived this formula, we're assuming we have equally spaced points for the Romberg integration. Now I have to admit, I'm not sure how different things would be if we had points that were not equally spaced and we tried to do Romberg integration. So I'm not so sure about that. It probably is a better approximation to the integral than trapezoidal rule by itself, but I just don't know how much better. So that's one point. The second point is, I do research, so I look at, in some cases, approximation to integrals depending on the experimental data that we have gathered. And usually the trapezoidal rule, I usually have enough points that the trapezoidal rule as an approximation to the integral is sufficient.
Sorry, it was very strange to see the windows that are for safety covered on that side.
I don't know. So I'm in the middle of a lecture here. It's an ad hoc recording, yeah. But I'll be done in just about 2 minutes, if that's cool.
No, I
Are you
understand.
you're teaching in here?
No, I'm support staff, but I will tell you just as for your ease of use, there are 2 mini studio lectures things that I've used in handy.
Okay, I just
I'm just so you know that make it easier for you.
right. I guess so. The way Class Tech asks you to do this is they ask you to reserve a room ahead of time and then schedule the ad hoc recording. And I just said I want any room that has Class Tech recording capabilities in EB 1, 2, or 3, and this is what they gave me. So, what are the studio rooms?
If you teach an engineering course, correct? Okay. They are associated with the distance online.
Yep. EOL.
Yeah, so there are 2290 over here. There's one in the EB2 West Wing. EB3 on the 3rd floor. 3204 is another one.
Oh, okay, cool. Thank you. Okay, I apologize. I was just interrupted really briefly, but I don't really have a whole lot more to say about this. Just, I guess the last thing I said was the trapezoidal rule usually tends to be sufficient for my integration purposes because usually I have a lot of points. And I've never tried Romberg integration in a research setting, and that's because, like I said, a lot of times my points are not equally spaced, and I'm not sure how much more it's going to give me. But suffice it to say, for this class, a lot of times we will do equally spaced points. So that's not something that you'll have to worry about, at least for this class. But it might be something that you might want to keep in the back of your head in the case that maybe you are faced one day with a situation where you have to approximate the integral without equally spaced points.